No, didn't talk to him yesterday. All right, finally got it to connect. I apologize for that. So we left off dealing with oxidation reactions. Let me find that right here. So we talked about alcohol oxidation on yesterday and oxidation up to the carbonyl. So we talked about the Swern reaction, chromic acid oxidation, uh, using TPAP, NMO as an oxidant for secondary alcohols, primary alcohols to carboxylic acids. We used potassium permanganate, and we said that the way that excuse me, the way that it works is through a process what we call hydrogen shuttling, where you can remove the carbonyl proton, which is this proton right here, right, and then you remove the hydroxyl proton, right. Those two protons get removed, and in the process you form a carbon oxygen pi bond. All right. So before we start talking about the next quadrant in the handout, which is dealing with reactions of carbonyls, we're going to talk about the Vedic reaction today. And then, but before we do that, I want to talk about reduction because it's a logical place to talk about this right here because it's kind of like the reverse of oxidation. So for carbonyl reductions, is the addition of hydrogen, right? So in this case, the way you reduce carbonyls to alcohols is kind of a two-step process. The first is you need a hydride, some type of hydride source, right? And the hydride is a nucleophile. It's a hydrogen with a pair of electrons that has a negative charge, right? And so the outcome of this would be first you would get a, let me change colors. I don't like that red. First you get a tetrahedral intermediate that looks like this, where the hydride has added, that's negative. This is R, and then the hydride is here. All right, so that intermediate then is quenched. So you add in some type of a weak acid, acetic acid, HCl, ammonium chloride, any type of proton source will quench this. So then that just picks up that proton. So you end up with an alcohol, right? And then the hydrogen there, right? So again, when you in order to get to the intermediate to get to here, it's just an attack, nucleophilic attack of your hydride. So this is just coming here like that, right? And there are a lot of different ways to do this. I think some of the ways that we'll see on the worksheet is we'll see LAH, which is lithium, aluminum hydride, right? That's a negatively charged aluminum. So it's got four hydrides around it, or four hydrogens around it. That's negative. And then the lithium is positive. It's a salt. So LAH is one really good reducing agent. Other reducing agents, sodium borohydride, so that's NaBH4. So LAH, sodium borohydride, and then there's also another called a dibal. Is Let me put a page in here. So dibal is diisobutyl ammonium hydride. I'm sorry, aluminum hydride. My bad. So it's aluminum. It's got two hydrogens, two isobutyl groups on it, like that, right? And it's negative. So dibal is another really good reducing agent. But all these do the same thing. They are a source of hydride, right? Or source of H minus. All sources of H minus, and when you put them in the presence of a carbonyl, they do what's called reduction, right? Remember, oxidation is increasing the number of bonds to oxygen or decreasing the number of bonds to hydrogen. Reduction is the inverse of that. It's increasing the number of bonds to hydrogen or decreasing the number of bonds to oxygen, right? So those carbonyl reductions, uh, when you see any of these reagents, LAH, NaBH4, dibal, anything like that in the presence of a carbonyl, then it's automatically understood that that's going to be a reduction. And you always have to have that second, that quench step. Otherwise, it'll just sit at the alkoxide, right? Because if there's a metal involved, like lithium or aluminum or sodium, it's just going to form a salt with that alkoxide that's there. So you have to quench it with a proton source to get to your alcohol. All right, so that's the first um, reaction that we're going to talk about with carbonyls. But today, that's what we're going to focus on is carbonyl reactions. All right, and let me see something right quick. So I know I have some questions in here dealing with that. All right, so let's look at these two reactions right here. All right, both of those reactions will be considered reductions. Right, you can see that LAH, then H2O. And the other case is sodium borohydride followed by methanol, which is also a proton source. Um, so let's see if let's predict the products. What will we get from this aldehyde if I treated it with LAH? Right, it's not going to touch anything except the aldehyde. Both of those are reducing agents. So what should I get? All right, we're gonna move on to the next reaction. Let me put this back how I had it too. And let me grab that from up here. All right, so the next reaction of a carbonyl that we'll talk about is the Vedic reaction. All right, so this reaction is the conversion of a carbonyl into an alkene. So you can see that the carbonyl right here got converted into an alkene. It can be a um, aldehyde or a ketone. You can do this type of reaction on esters, but it's with a different set of reagents. So you go from a carbonyl to an alkene. And again, uh, as far as knowing the reactions, it's really important that you know your functional groups. If you don't know your functional groups, or if you still wishy-washy on that, then it makes this even harder. But if you know your functional groups, then it's not as difficult, because when I say a carbonyl to an alkene or a ketone to an alkene, then you know what both of those are, and then you kind of can see where it's going. All right, so in layman's terms, I'm gonna give you a shortcut way to think about this first, and then we're gonna actually go through the mechanism. Right? So these are your reagents, right? You need an alkyl halide. I shouldn't do that in pink. You need an alkyl halide. You need triphenylphosphine, and then you need a strong base. Those are the three things you need in addition to your carbonyl to do the Vedic. Right? You need an alkyl halide. You need a phosphorus source. In this case, it's triphenylphosphine. That's just 3 benzene rings around phosphorus. And then you need a base, right? And you've seen this base before. This is potassium terpbutoxide. It's just oxygen bonded to a tert-butyl group is negative. It's really basic. Like, the more bulky your base is, the more basic it's going to be. So, and the less nucleophilic it will be. Right. So you want this to be looking for protons, not looking to react with other electrophiles. So you need those three things. When you see that set of when you see this in the reaction mixture, that's a dead giveaway that is going to be a Vedic reaction. If you have a carbonyl present, all right, that's a dead giveaway that is going to be a Vedic. So the shortcut way to think about this is, if you look at the alkyl halide, right? and you subtract out one hydrogen plus the halogen, what you're left with is what's going to replace oxygen in that carbonyl. So this is basically what you are left with here is CH2. Are y'all following that? It's not math in the traditional sense, but if you remove an H and you remove the Br, what you're left with is what's going to replace oxygen. Right? That's going to replace oxygen.
Yes, that makes sense.
In the carbonyl. So whatever my carbonyl is, let's just take just a basic ketone, right? And if methyl bromide is my alkyl halide, then what I'm going to be left with is this. Right? I'm going to show you how that works, but this is just a quick and dirty way to think about it. And it's always the carbon that's bonded to the halogen, the most electrophilic carbon. It's not, if that was a long chain, it wouldn't be any other carbon in the chain except the one that's bonded to the halogen. We'll do another example where you'll see that. All right, so this happens through what we call an illet. That's this species down here. It's a two atoms adjacent, one positive, one negative. So opposite charges, but they're adjacent to one another, right? But before you can do the reaction, you got to make the illet. So let's go ahead and let me see. I got room. I'm gonna shrink this. All right. All right. So we gotta. Again, before you could do the reaction, the illet has to be made. And I can say this as a grad student, this is probably the easiest reaction I ever did as a grad student. I forgot what I was making. I was making something, but this is a reaction where you set up uh, the illet formation first, let it run for about an hour, then you come back, syringe in your aldehyde or your ketone to make the double bond, right? So to make the illet, that's the purpose of all that stuff over the arrow are your reagents for the illet formation, right? So if you take and I'm going to draw this out in Lewis form to make it, I'm going to put the bromine on the other side just to make it make sense. So that's my alkyl halide, and I'm going to react that with triphenylphosphine. Phosphorus has a pair of electrons, and so I'm going to come in and do a SN2 substitution on the alkyl halide. All right, so what I'm left with is this CH3 and then this is PH3, and that's positive now. Carbon is still neutral, and then plus bromine, which is out here kind of like a salt, right? You got a plus charge and a negatively charged atom somewhere floating around. It's gonna find that plus charge and make a salt with it. So then now this is where I need my base. So if I add in my base, which up here we use potassium terpetoxide, so I'm gonna draw that in here. This is negative. And then potassium. Sorry about that. Potassium is here. So then I want to pull off this proton. So it's just a proton transfer. If you notice, all the terminology for all the different types of reactions is the same. Substitution, elimination, proton, all those reactions we learned. Now it's like this is the kind of multiple applications of those reactions. All right, so now this is just a proton transfer, right? That's the purpose of the base, to rip off that proton, and now you have carbon with a pair of electrons, and this negative. That's that, and then the illet, which is positive. Now, can you see what I mean? You took off a H, you took off the Br, and so this is what you have left. All right, so now what you're left with side product wise is KBr and then terbutanol, which all goes in the trash, right? We don't care about any of that stuff. All we care about is the illet. And the beauty of this is it's a one pot reaction, right? So if I set this up in a flask, I don't care about the KBr floating around in there. I don't care about the terbutanol, none of that. All I care about is this, the fact that I have that now. And so now what I'm going to do is take the illet. I'm going to run out of room. I got to shrink this. I'm going to take the illet and I'm going to react that with my aldehyde. All right, so let me, you know what? I'll just add a page. So I'm going to just copy that illet. And oh, not like that. All right, so I got my illet now. And this is the second phase of the reaction. First phase is illet synthesis. Right, that's the first phase of the reaction, is to make the illet. Second phase is to react the illet with your carbonyl, whatever it may be.
Dr. Russell, you said the
Yes,
first phase was to make the what?
the illet. Yeah, right here, illet synthesis.
Okay.
Yep, and then the second phase is the attack on the carbonyl, which we're gonna see in a second. All right, so your illet is really a nucleophile. You got a carbon, you got a negative charge on carbon. So that if you put a nucleophile around the carbonyl, we've already seen what's going to happen. The nucleophile is going to attack the carbonyl. So if I bring in, I'm just going to use acetaldehyde. If I bring this in uh, as my carbonyl source, right? The first thing that happens is the illet is going to take that pair of electrons and boom, attack that carbonyl, right? So that's the first part of that reaction. And the second part, what you do is when you're running this, is you come back after some time after you've allowed the triphenylphosphine and the base and the alkyl halide to stir together for some time. You come back and you just take a syringe and you syringe your aldehyde in slowly, just not necessarily drop wise, but you don't want to hose it in there either, right? And so when that aldehyde encounters the illet, this is the reaction that happens. So now I end up with this and just follow this. So here's the CH2. That carbon now is bonded to the aldehyde carbon. And it's a similar type of deal. It's a tetrahedral intermediate after you expose that aldehyde to a nucleophile, right? And then here you have P pH 3, and that's still positive, right? Now there's some debate on whether or not this actually happens, right? There's some debate on whether or not it's stepwise like this or if it's concerted. But for the purpose of this class, we're just gonna follow a logical progression. I don't want to get too deep in the weeds on it. I may already be too deep in the weeds. Um, so this is what's known as a beta-ene, right? Again, it's debated whether or not that actually forms. That was the original thought, was that you went through a beta-ene, but then some more research was done, more investigation was done on the reaction, and it was shown that it actually goes through kind of like a concerted reaction in order to form the next step, which is the what we call the oxophosphatane. So what do you think in this case? You got a negatively charged oxygen, you got a phosphorus next to it with a positive charge that can be hypervalent, so it can form up to 5 bonds. What do you think is going to happen? Again, you always want to be thinking, where's my nucleophile? Where's my electrophile? Right? That's all we're doing. Everything here is nucleophile electrophile chemistry or acid-base chemistry. So what do you think? This is the key step in the reaction, as a matter of fact. Well, one of the key steps. So if phosphorus is your electrophile and oxygen is your nucleophile, what do electrophiles and nucleophiles do when they get around each other? Right? They react, just like the carbanion over here reacted with the carbonyl. So this actually closes up, and so now you end up with this species, right? And the CH3 and the H are still here, and the two hydrogens on this carbon are still here. Now let me clean that up. Right, and now this is new. Everything is neutral now. So all the charges are neutralized. You still got 2 lone pairs on oxygen, and this intermediate is observable. Right, the beta-ene is debatable whether or not you can observe that in a reaction, or has been observed. Um, and actually, one particular chemist, Peter Wilf, actually showed that the beta-ene didn't exist. But we're going to use it because it helps to make sense of what we're talking about. All right, so this is the oxophosphatane. Right, that is the intermediate that's going to, can you see, kind of, we're almost to the point now where if you put a double bond here, you can see your alkene already, right? So how would we get a double bond there? This is also a key step. Like in this step, when mechanistically, like with this reaction, it's always the ring closure followed by decomposition of the ring. Like those are the two steps that are competing when you think about making cis alkenes or trans alkenes, right? It's always one of those two steps that determines what the uh, major product is. But here it doesn't matter because this can't be cis or trans because it's monosubstituted. But what do you think? How can I put a pi bond there using what I already have? I need some electrons from somewhere. Am I right?
From the oxygen.
Okay, those are kind of too far away, but I can use one of the bonds, right? I can use this bond right here and break it and put a pair of electrons there. And I can take this CO bond and break it and give those electrons up here. Sorry about that. I can do that. And that's what happens. It actually decomposes like that. And that's where your alkene is going to come from. So you're going to end up with this. And I'm writing it out in Lewis form so we can keep track of all the atoms. So you end up with that and this. Plus the phosphine oxide. This PO double bond drives the reaction. That's a really strong bond. So it's driving the decomposition of that ring is actually driven by the fact that you get this PO double bond in the product because that's a really, really, really strong bond. So it gives off a lot of energy when you make it. Um, and then your alkene is your main product, though. This is what you're trying to get to. Right? So the way it works, first you make the illet, and then you react the illet with the carbonyl. Right? And that's how it reacts. It attacks it as a nucleophile, then you cyclize, and then you decompose to get the alkene. All right. Any questions about that? Again, the shortcut way to think about this is subtracting out HX from whatever your alkyl halide is. What you're left with, that's what you replace oxygen with. Right. Let's look at an example of this. Actually, we can look at a couple of examples. Yeah. We're going to start on this wheel right here, and then we're going to come back to the hemiacetal stuff. All right, so let's go here. Let's do this part. Let's do this reaction first, and then followed by the addition of methanol. Let's do that first. All right, so what would I get if I took that primary, this is a primary alcohol. What would I get if I took that primary alcohol and reacted it with potassium permanganate? Look at the sheet with the four quadrants. And here are your choices up top. One of them is epoxidation, which is, and then oxidation, and oxidation followed by the Vedic, and then we already did the ether formation, so I'm gonna cross that out. All right. So what type of reaction is that if I take a primary alcohol and react it with potassium permanganate, which is a superoxidant that we talked about on Monday?
A swern?
It's not a swerm, but it is in that class of reactions. Thank you. It is it's in the class of alcohol oxidations to carbonyls. But right here, so if it was a swern, that you would see those reagents. You would either see swern or you would see DMS and DMSO, sorry, and oxalochloride as your reagents. But you're close though. It's in the same class because it's oxidation. Right. So potassium permanganate converts alcohols into carboxylic acids. All right. So let's see what we get from that. All right. So that first product is going to look like, I'm going to abbreviate this benzene ring as a phenyl. That's the alkene is still intact. But when I get here, that alcohol is actually going to become a carboxylic acid, right? Because I treated it with potassium permanganate. All right. So what I did was I oxidized this alcohol up to the acid. So that's what this does. So it oxidizes primary alcohols to the acid. I had to abbreviate that. All right. Now if I take the acid and react it with an alcohol like methanol, what kind of reaction is that? So I have a carboxylic acid, and I'm gonna let me put some other reagents over here. We're gonna heat this up, and we're gonna add in some H plus. Right? It can be from wherever. We can add in some HCl. We can add in a little bit of acetic acid, TFA, trifluoroacetic acid. But we need a proton source to catalyze it. So what type of reaction is that? You got choices up top, I think. You got one of the choices. So we know we did oxidation. What happens to carboxylic acids when you react them with alcohols? Is that not going to get converted into an ester? That's a transesterification. Am I right?
Yes, I see that now.
It's the first reaction we did. Right. So when you take a carboxylic acid plus an alcohol, you warm it up in the presence of an acid catalyst, you're going to get transesterification. I'll fix that later. All right. So when you think about the transesterification, kind of a shortcut kind of way of thinking about that is to look at whatever that alkoxy group is. Whatever that group is, that's what's going to replace the OH group on the acid. All right. All right. Let's do the next reaction over here. I got chromic acid, primary alcohol. What I'll get from that? Look on the handout, the bottom left quadrant. What does chromic acid do to primary alcohol?
Will be a aldehyde.
It's going to convert it into an aldehyde. Great. Thank you. I'm gonna cheat. I'm gonna copy this from over here. So it's going to convert that into an aldehyde. Very good. I'm gonna fit that right up in that little spot. All right. Now I got an aldehyde. After that first step, that's an oxidation. What about the second step? What kind of reaction is that? You got an alkyl halide, you got triphenylphosphine, you got strong base. Right? Anytime you see this group of reagents together, alkyl halide, triphenylphosphine, and a base, which we just did like 2 minutes ago. It's going to be a Vedic. In the presence of an aldehyde, that's going to give you a Vedic. Might have been 1 minute ago. What's the outcome? What does the Vedic reaction do to carbonyls, specifically to aldehydes and ketones, even though it works on other types too?
It'll be an alkene.
It's going to convert it to an alkene. Without going through the mechanism, which of the, look at the two carbons in the alkyl halide. Thank you for that too. Look at the two carbons in the alkyl halide. Which one did I say is the carbon that's going to replace oxygen and make that aldehyde into an alkene?
The CH3.
It's always the carbon that's connected to the halogen.
Right.
So it's the CH2. So
yes.
what's the shortcut? Let's think about that. What am I taking off of that molecule to get it ready for to substitute that oxygen? Remember I said if you take I'm gonna just write this out like that. If you take, because that's what that looks like. And it's always the carbon, that carbon that's bonded to bromine is activated because of the dipole. The CH3 is not. So we're not gonna touch that. All right. And I said we need to subtract out what? HX, whatever X is. In this case, X is bromine. So what I'm left with is that. Am I right?
Yes.
Plus HBr, which I don't care about. So when I make the alkene, this carbon right here is going to replace oxygen, right? And I can do that without knowing how the mechanism works. I can actually predict the product based on this little shortcut, right? Without knowing how it works. If I take a H and a X off of my alkyl halide and take it off at the right place, then I'll know which carbon to replace that with. So that product is going to look like this. Let me erase all this other crap. So that is going to be carbon, and it's going to have a hydrogen on it. So H, CH3. Right. The reason I had to take that other H off is because if I don't, you can't stick CH2 at that position because it's going to have too many bonds to it. Right. So we oxidized up the carbonyl, and then we did a Vedic. Right. And that in the Vedic reaction, that actually converted the carbonyl into an alkene. Right. And it's always the oxygen that's going to get replaced. I don't want to say substituted because you can't do substitution at a sp2 atom, but you can do addition followed by elimination, which is exactly what this is. We did an addition. Let me go back up to here. You can see that first step is addition, and then the subsequent steps lead to elimination. And I'll buy you lunch if you could tell me what the key characteristic is for elimination. Like, what do you always get? And we got to stop here. So
I mean, I know it, but I don't want to. I want to give somebody else a chance.
Okay. Yeah, that's good. That's good. I like that. That's very noble of you. Is your mic broken?
Thank you. But somebody said something in the chat
No,
too.
I'm just in the car.
Okay. Yeah, that's a good place to be. Yeah, you're right. You always get a double bond. All right. So that's the hallmark of elimination. You get either a double, sometimes it can be a triple bond too, but you get a pi bond at the end of the reaction. So you can put your cash out. That can go in the chat. You don't have to say that out loud, but you can put that in the chat. But yeah, so that's what this is. It's an addition followed by an elimination. That's why you get a
Thank
pi
you.
bond. Yeah, no problem. All right, we're gonna stop right here. I'm telling you, this is not gonna click unless you're getting reps. Reps means that you're looking at this before you come, after you leave, because I promise you, these reactions are not gonna come by osmosis. You can't put the paper on the pillow and sleep on it and think it's gonna come. You gotta get reps. And that's the whole purpose of doing it this way, immersing you in it so that we talk about it and then we go find the reactions and we do them. So the only way that this is gonna click in these last 2 weeks is for you to see this repetition over and over again. That's why I said to make flashcards. Because you need to be able to recognize the reagents, right? Because that's a big, the reagents and then recognizing the functional groups. That's huge.
Dr. Russell,
Mhm.
are you gonna post any YouTube quizzes?
This, it should be already open. Isn't it already open?
The last time I checked, I didn't see it, but that was a minute ago. So
All right,
maybe I can check.
let me make sure it's open. I'm gonna stop now and I'll do it before I start my next class. Make sure that quiz, because there are definitely 2 quizzes. I think it's 1 or 2 quizzes for this section, but I'll check now. All right, so I'll post the, go ahead.
Yeah, I only see one.
Yeah, it should be up there already.
All right.
Yeah, so make sure you take that and that video that I sent, make sure you watch it, man. You can watch it more than once. If you don't want to watch it, you tired of my voice, go to the syllabus, and this whole section is outlined with problems and section numbers for each chapter, because these reactions coming from all different chapters. So however you want to do it, but you can't float through this part. All right. If there are no other questions, you can log out. I'm gonna go ahead and stop recording too. I don't want them to hear me chiding you all. Sometimes you need that.